cosmic microwave background, and the early universe's signature. The baby picture with a secret. While deep time wrote clues into rock, the early universe wrote them into light. The cosmic microwave background is the baby picture. Photons launched when the universe cooled enough for protons and electrons to hold onto each other. That last scattering moment froze ripples into a mottled pattern across the sky. Hidden in those ripples is a ledger of the constants that set the rules back then. Here's the stake. Change the fine structure constant in that hot plasma and you move everything. How tightly atoms bind, how often photons scatter, the exact timing when the fog clears. Those details shape the angular power spectrum, the peaks and troughs that Planck and WMAP mapped with ridiculous precision. Shift alpha and the peaks shift with it. Screenshot this. The baby picture has metadata. Touch alpha, the CMB edits itself. Action first. Satellites spent years scanning the whole sky, stripping out foregrounds, calibrating detectors, and collapsing 1 billion temperature measurements into a spectrum. The first acoustic peak tells you the size of the sound horizon, how far pressure waves traveled before recombination. The second and third peaks tell you the ratio of baryons to photons, the amount of dark matter, the damping at small scales where diffusion erases contrast. All of this is sensitive to how easily electrons and protons meet and stay together, which depends on alpha. Make alpha larger and hydrogen binds more tightly. Recombination happens a bit earlier. Photons decouple sooner. The sound horizon is smaller. The peak positions slide. Planck teams fit models to this spectrum, not by eye, by exploring a high-dimensional parameter space. The standard set includes 6 core parameters. Add a knob for alpha, let it float, and ask the data how much wiggle room is left. The answer is, not much. If you keep the rest of the model intact, flat geometry, cold dark matter, a cosmological constant, the CMB locks alpha near the present value within a few parts per thousand at recombination, and fixes H0 near 67 km/s/MPC in that framework. That's a broad brush compared to the quasar ppm whispers, but it's at a time 380,000 years after the Big Bang, when the physics was very different. The early universe says, you can't move alpha far without messing up the peaks. But there's a catch, the degeneracies. Vary alpha and you don't just move one dial's output. You can partly compensate by adjusting the baryon density, the Hubble parameter, or the scalar spectral tilt. That's the model dependence trap. If alpha creeps, the fit can shove other parameters to soak up the change. The spectrum still looks good, but your measurement of alpha now depends on choices under the hood. Planck papers spell this out. Constraints tighten or loosen depending on what else you allow to float. Meanwhile, polarization adds a second witness. The E-mode polarization peaks arise from the same acoustic physics but respond differently to scattering. Fold in polarization, and the parameter covariances shrink. You get sharper bounds on recombination history, hence on alpha then. The fits still say small wiggle room, percent level at most, but the path there shows how interlocked the constants and cosmological parameters are. Here's where the human debate gets loud. One side, the CMB kills large variation, end of story. The other, careful. You've assumed a cosmological constant, fixed neutrino physics, and no exotic couplings. Relax those and alpha's leash lengthens. Papers trade scenarios. Allow early dark energy, allow extra relativistic species, allow a time-dependent dark energy equation of state. Each one stretches or tightens alpha's corridor. While that's happening, a deeper point bubbles up. The CMB is mostly sensitive to dimensionless combinations, ratios that don't care about units. That's a sanity check. Change a dimensionful constant like c by definition and you're just changing your ruler. What matters are the pure numbers. Alpha, the electron-to-proton mass ratio, the gravitational strength in Planck units. The CMB, like the quasar spectra, cares about those. Impact. Even with degeneracies, the early universe sets guardrails. No model where alpha wandered wildly through recombination survives without breaking the peak structure. That pushes theorists toward gentler evolution or spatial variations that average out over the last scattering surface. It also feeds back into the quasar dipole story. If a spatial gradient exists today, was it present at recombination? If yes, it would imprint a preferred direction in the CMB. Planck's sky does show mild hemispherical anomalies, but nothing cleanly aligned to an alpha gradient. That tension forces any dipole mechanism to be subtle, maybe the field rolled after recombination, or the effect couples weakly to photons at early times. Complication keeps circling. Recombination physics itself is a careful enterprise. Multi-level hydrogen, helium, 2-photon decays, radiative transfer in the Lyman lines. Teams like Cosmo-Rec and High-Rec built detailed codes to get it right. A small misstep there can masquerade as a constraint on alpha. So the community did the boring, necessary work. Independent codes, cross-checks, validation against laboratory measurements of atomic rates. The conclusion stayed steady. Within these improved recombination models, there's limited room for alpha to move at Z110. Human beat. Picture the group huddled over a residual plot at 3 p.m. in a windowless Planck office, arguing over a 0.2% bump at multipole L120. The bump vanishes when they tweak a foreground model. Relief in the room, but also fatigue. They've been hunting ghosts for months because they know any whisper of drift could hide in the same bin as a dust template error. Meaning lands like this, the CMB doesn't settle the constant question, but it fences the playground. It says the early universe wasn't wildly different in the electromagnetic rules. That's not the same as saying the rules never drifted. It sets the stage for theories where constants are fields that barely moved at recombination and may have slid later or vary in space more than time. Thumbnail line, the baby universe says, not too much. Early guardrail set, now stress test the limits. If alpha is on the table, people ask the reckless question next. What about the speed limit itself? If C isn't fixed, causality and the whole cosmological story twist. That's where the mavericks walk in. Speed of light theories, VSL versus inflation. The speed limit might be a setting. If light was faster before, your map of causality is wrong. Here's the stake. If the speed of light isn't fixed, causality and every deep assumption in cosmology gets a stress test. The horizon problem, the question of how opposite ends of the sky look the same when light shouldn't have had time to even the temperature, suddenly has a different door. If C was larger in the early universe, information could have flown fast enough to iron out the wrinkles. No inflating space needed. That's why the idea keeps returning, even when the room gets chilly. Action starts at the end of the 20th century. A handful of theorists, tired of patching the standard model with just-so beginnings, wrote down varying speed-of-light theories. Moffat, Albrecht and Megiddo, Barrow, they sketched dynamics where C depends on a field that took different values in the early universe. In those models, C relaxes to today's value, leaving a uniform cosmos behind. The math wasn't a handwave, it was a program. Modify the Einstein equations or the matter sector so that the causal structure changes at high energies, then recover the usual light speed later. Meanwhile, inflation was already winning. A brief, furious expansion early on solves the same horizon and flatness problems by stretching a tiny, uniform patch to cosmic size. Inflation predicts a near-scale invariant pattern of primordial fluctuations, something the CMB sees. It gives you a mechanism for seating structure. It even explains why space looks flat without needing a fine razor balance. VSL had to compete with that record. Here's where it gets interesting. VSL isn't one theory, it's a family. Some versions keep Lorentz invariance locally and let C vary cosmologically through a scalar field that changes the effective light cone for certain interactions. Others break Lorentz symmetry outright in the high-energy regime and glue it back at late times. Some fiddle with how units are defined. Others anchor everything in dimensionless ratios and embed C variation in something you can actually measure, like how alpha or the horizon scale behaves. Then the complication that kills many conversations: units. If you change a dimensionful constant by declaration, you might just be changing your ruler. Physicists guard against that by asking, what dimensionless observables move? The fine structure constant is dimensionless. The ratio of the sound horizon to the angular diameter distance is dimensionless. VSL devotees know this. The careful ones translate every claim into those ratios. The careless ones get eaten in seminars. Meanwhile, inflation isn't bulletproof. It solves problems, but it raises others. Which potential drives it? Why that slope? Why that initial condition? Some versions produce eternal inflation and a multiverse you can't easily test. Observationally, Planck boxed in many simple inflation models and saw no obvious primordial gravitational waves at the levels some hoped for. That opened a small window where alternatives like VSL could pitch. Maybe there's a different causal story with fewer untestable branches. Nobody in polite company says, "What if C moved?" But the math lets you ask it. Human beat, get this. One of the most vocal VSL advocates walked into a top-tier department and wrote C equals CT on a board. Someone snorted. He kept going, chalked dust on his sleeve, mapping how a time-dependent speed of light in the early universe could generate the right spectral tilt. 10 minutes in, the laughter stopped. Not because he won, but because the math closed and the predictions landed in ranges you could compare to data. Impact? Even if VSL never dethrones inflation, it forces clarity. It makes inflation defenders specify what's essential and what's convenience. It pushes everyone to tie claims to dimensionless signatures and to spell out which sectors like cone they mean. Photons, gravitons, both. It also connects to our earlier thread. If constants vary because of fields, those fields can couple to electromagnetism and gravity differently. A universe where alpha drifts and C shifts might be two facets of one rolling field. Observational tests bite back. The CMB's acoustic peaks anchor the sound horizon, which depends on C and the plasma's properties. Baryon acoustic oscillations in galaxy surveys measure the same scale frozen into matter. If C was wildly larger at recombination, you'd expect a mismatch unless other parameters compensate. Some VSL models build that compensation in. Others die on the spot. Polarization patterns, lensing of the CMB, Big Bang nucleosynthesis yields of light elements, all add constraints. And multi-messenger constraints bind late-time deviations. The neutron-star merger GW17081-7 showed gravity and light speeds agree today to astonishing precision. You can't crank C without knocking these down like a row of dominoes. There's also the gravitational wave frontier. If gravitons felt a different effective speed in the early universe, primordial gravitational waves and their imprint in B modes would shift. LIGO's multi-messenger event from a neutron-star merger measured the difference between gravity and light speeds today to absurd precision. No room for late-time deviations. That pushes viable VSL into early epochs and into models where speeds converge quickly. Meanwhile, the unit choice trap keeps reappearing. A good sanity check. Phrase everything in Planck units where C, H-stroke, and G define the scale. If you let C vary there, you're really letting the mapping between those units and matter's couplings move. That circles you back to the dimensionless constants, alpha, the mass ratios, the gravitational strength compared to particle masses. The story keeps pointing to them as the honest currency. Human moment, a grad student skeptical of VSL tries to reproduce a key plot from a VSL paper late at night. The curve won't match. They email the author expecting a brush-off. Instead, they get a notebook and a candid note. Here's the catch. If you don't vary the electron mass with C, you'll break BBN. Try this coupling. The student runs it. The curve lands. Doubt remains, but respect grows. Meaning threads through the debate like this. VSL isn't heresy for sport. It's a pressure test on our comfort with fixed rules. Inflation earned its place by prediction and consistency. VSL earns attention when it ties itself to clear, testable, dimensionless consequences and survives the crossfire from CMB, BAO, BBN, and gravitational waves. Most versions won't. A few might. Hook. What if light was faster before? Screenshot this. If you vary units, you fool yourself. Vary a pure number, you change the world. And here's the pivot we need. Talking about C reminds us that the constants that really matter for change are the pure numbers. If anything's going to drift in a way we can trust, it'll be those dimensionless combinations that set chemistry, spectra, and stars. That's where the chase tightens next. Dimensionless truth, why only certain constants matter. Numbers you can't redefine. If it's not a pure ratio, it's a ruler trick. Here's the pivot we've been circling. Only certain constants are even allowed to change in a way that means anything. If you tell me the speed of light changed, but you also changed the length of your ruler and the tick of your clock, you didn't discover new physics, you rewrote your units. The honest currency is dimensionless. That's where reality hides the numbers you can't rescale away. Alpha is one of those numbers. So is mu, the proton-to-electron mass ratio. In gravity land, you can recast G into Planck units and ask about the strength of gravity relative to the rest of physics, another dimensionless measure. These ratios are the ones that sculpt chemistry, spectra, and stars. Move them and you move the world. Action starts by tightening the target list. Alpha sets the spacing of spectral lines and the chemistry playbook. Mu decides how heavy molecules vibrate and rotate, because the nuclei's inertia sets the beat. The gravitational coupling, written as G times the proton mass squared over h/c, tells you how strong gravity is compared to quantum forces. If you want to know whether the periodic table stays familiar or stars burn the same way, you track alpha, mu, and gravity's dimensionless strength. Now what happens if you nudge them? Let alpha slip by a few parts per million and atomic energy levels shift. Double bonds stretch or compress. Reaction rates change by measurable ticks. Colors of absorption lines drift. For mu, small changes move molecular lines more dramatically because vibrational and rotational energies scale with reduced mass. That's why cold clouds of molecules, ammonia, methanol, hydrogen, become microscopes for mu across the universe. Gravity's dimensionless strength threads through stellar structure. It sets how massive a star must be to ignite, how long it lives, how pressure balances against collapse. Push it and you redraw the Hertzsprung, Russell diagram. Observers went hunting with this in mind. Radio astronomers tuned to methanol and ammonia lines in distant galaxies. Those lines have different mu sensitivity coefficients. Compare them and you get a direct probe of mu at redshifts of half the universe's age. In some systems, the offsets land within a few parts per million of today's value. In others, the uncertainties are bigger, tangled with cloud dynamics and velocity structure. That's the complication. Molecules live in messy places. You need multiple transitions, multiple species, and clean kinematics to avoid fooling yourself with two clouds at slightly different speeds masquerading as a constant drift. Meanwhile, optical spectroscopists chased molecules in the ultraviolet, molecular hydrogen toward quasars. The lines are faint, the forests thick, but the payoff is high. H2 transitions carry different mu sensitivities, so a pattern across dozens can shout or silence a drift. Some analyses claimed hints at ppm level changes. Others, with improved calibration and more conservative line selection, flattened them to consistent with zero. The story rhymes with alpha S. Signals flirting with significance, systematics rushing the stage, teams arguing over which lines to trust. Back on Earth, precision labs joined the chase. Spectroscopy of simple molecules, HD+, H2+, trapped and laser-cool, ties mu to frequency standards. Pair that with optical clocks and you can measure drifts in alpha and mu simultaneously by comparing carefully chosen transitions. One more alpha-sensitive, one more mu-sensitive. That's not just clever, it's necessary. If both move, a single ratio can hide a conspiracy. 2 or 3 ratios break it, revealing which number slid. Human beat. A spectroscopist pulls up a fit to 80 molecular lines at Z2. The residuals look random, but a colleague points to a subtle trend with wavelength. That's a calibration comb's fingerprint sneaking in. They redo the reduction with a laser frequency comb reference. The trend dies. Their claimed non-zero mu drift drops by half, now within the error bars. It's a small heartbreak, but it's also the culture. If you can kill your signal with better calibration, you must. Off camera, someone says, don't tweet it. Impact radiates outward. The tighter the mu and alpha bounds get, the narrower the path for theories where a scalar field couples to electromagnetism and the strong force. A rolling field that nudges alpha will typically nudge quark masses too, and through them mu. Equivalence principle tests then feel it as an extra force depending on composition, a fifth force. Torsion balance experiments and lunar laser ranging hammer those couplings. If you want drift without a fifth force detection, you have to thread a needle. Couple weakly to matter here, more strongly to photons far away. or let spatial variations live where our instruments are. Here's a subtlety people don't say out loud at first. The constants might co-vary to keep some observables nearly fixed. Screenshot this. Two sliders can fake a straight line, drift together, and the resonance looks stable until a different test yanks the mask off. That's not magic. It's a model where one field controls multiple couplings. You can hide a lot from Oklo and stars if knobs turn together, but the hiding isn't perfect. Different systems, atomic clocks, molecular clouds, stellar nucleosynthesis, pull on different combinations. Cross-compare enough of them and the conspiracy unravels. Smoking gun, cleaner than rhetoric. If you can measure it without changing your ruler, it's real. And if it's real, it can move. The gatekeepers know this. That's why they spent decades treating constants like sacred objects. Because once you admit only pure ratios matter, you admit those ratios can slide. Not by decree, by data. Meaning lands here. Chasing dimensionless constants keeps us honest. It strips away unit games and forces any claim to show up in ratios nature actually cares about. It also clarifies the stakes for life. Change alpha and mu beyond tight windows and chemistry becomes unrecognizable, stellar furnaces misfire, planet formation shifts. The universe looks tuned not just in one number, but in a web of them. From numbers to furnaces, if the knobs twitch, stars shout. And now that web feeds the next question. If tiny shifts in alpha and mu could tilt chemistry and fusion thresholds, what does that do inside the cores of stars, where small nudges meet huge consequences? Stellar hearts and nuclear thresholds on edge. The recipe for carbon has a hidden knob. Move one digit and a billion worlds go hungry. Inside a star, constants aren't abstractions, they're levers. A few parts per million in alpha or mu, and the nuclear thresholds that decide what a star makes, how long it lives, even if it ignites at all, start to slide. That's the stake. A whisper at the fundamental level magnifies into a shout in stellar cores. Action begins with a fragile miracle: carbon. Most carbon in the universe comes from the triple alpha process. Two helium nuclei collide to form a shaky beryllium-8, which usually falls apart in a blink. But if a third helium arrives fast enough, and if the combined system passes through a very specific excited state in carbon-12, the Hubble resonance, the reaction sticks. That resonance sits at just the right energy to amplify the reaction rate by orders of magnitude. Move it a little, and the stellar recipe changes. Here, S where alpha enters. The position of the Hubble resonance depends on the balance between the strong nuclear force pulling nucleons together and the electromagnetic repulsion between positively charged protons pushing them apart. Nudge alpha up and you strengthen the repulsion, sliding the resonance. Nudge it down and you ease it. The sensitivity isn't dramatic in everyday lab terms, but in fusion it's ruthless. A few tens of key V shift in the resonance energy can throttle carbon production or send it into overdrive, altering how much oxygen follows in the alpha capture chain. Modelers have mapped this terrain. Run stellar evolution codes with slightly different fundamental inputs, and you watch the carbon-oxygen ratio at the end of helium burning swing. Too much shift and you get stars that overcook carbon into oxygen and heavier elements, starving carbon-rich chemistry later. Too little and you pile up carbon, starving oxygen. The allowed window isn't razor-thin, but it's narrow enough that a drifting alpha is playing with the knobs of life's pantry. Meanwhile, gravity's dimensionless strength sets the stage for which stars exist to do this dance. Change it, and the minimum mass for hydrogen ignition moves, the pressure balance in cores rewrites, and lifetimes bend. Long-lived, steady-burning stars like the Sun rely on a precise tug-of-war between thermal pressure and gravity. If gravity relative to nuclear scales were stronger, stars would be smaller and faster burning. Weaker, and many wouldn't ignite or would linger too long, never forging enough heavy elements. Back in the core, other thresholds lurk. The proton-proton chain that powers small stars and the CNO cycle that takes over in heavier ones have rates that depend sensitively on tunneling probabilities and reaction Q values. Those depend on nuclear masses and electromagnetic barriers. Small shifts in alpha and in quark masses ripple into those rates. You don't need a big change to move a star's convective boundaries or to alter when shell burning ignites as it ages. Human beat. A theorist spends weeks nudging a resonance by 25 key V in a code, watching the output carbon-oxygen ratio tick from 0.3 to 0.7. Knuckles crack, a tired grin, because that's not just a number, it's the chemistry of future planets. In the next office, a nuclear physicist wrestles with lattice QCD outputs that tie quark masses to nuclear binding energies, arguing over uncertainties that look tiny on paper but stretch into a factor of 2 in a star's fate. Down the hall, someone stares at sensitivity curves, derivatives that say if alpha shifts by X, the reaction rate shifts by Y, and feels that steady, quiet pressure. Digits matter. Complication shows up with the anthropic whisper. If the Hoyle resonance is so finely placed, some say, of course it must be tuned or we wouldn't be here to ask. But the physics path doesn't end with a shrug. You can build models where a scalar field controls multiple couplings so that the strong and electromagnetic pieces co-vary, keeping the resonance near useful values even if individual constants slide. That buys you stability but not infinity. Push too far and the conspiracy fails. Different parts of nucleosynthesis feel different combinations, and the mismatch shows. Observational threads are starting to tug on this. White dwarfs, the carbon-oxygen embers of sun-like stars, carry a memory of the carbon-oxygen balance they were born with. Astroseismology, reading their pulsation modes, can probe that balance. If constants drifted enough to tilt fusion thresholds over cosmic times, you might see trends in white dwarf interiors across populations. It's early, it's messy, but it's a path where stars themselves become detectors. Meanwhile, supernovae sit at the end of this chain as brutal auditors. Type Ia supernovae rely on carbon-oxygen white dwarfs reaching a critical mass and igniting runaway fusion. Change the carbon-oxygen ratio or the ignition conditions, and the light curves. Our distance ladders shift. If constants drifted enough to alter that ignition threshold over billions of years, the standardization we trust would wobble. That loops back to cosmology's tensions and keeps everyone honest. You can't change nucleosynthesis without risking your yardsticks. Here's a micro story. A code crashes at 3 a.m. because a resonance drift pushed a reaction rate out of a table's bounds. The grad student fixes it, reruns, and watches a population of stars live 1 million years shorter. It's a footnote in a draft, but it's also a reminder. Thresholds in stars are cliffs, not ramps. The quiet horror is this. A ppm nudge here echoes as 1 billion fewer worlds there. Impact lands wide. Stellar lifetimes, element yields, the habitability clock of galaxies, all lean on thresholds touched by alpha, mu, and gravity's relative strength. If those numbers drift, even in parts per million, integrated over billions of years and through billions of stars, the universe's chemical story bends. The web of feedback tightens. Oklo constrains the past locally. Quasars tease spatial tilts. Clocks police the present. Stars magnify small differences into astrophysical consequences we can, in principle, read. Meaning then, the universe looks tuned not just because one number sits pretty, but because many sit in a coordinated range that lets fusion teeter at the right edges. The question isn't only whether it's tuned, it's whether it's tuned and stable, or tuned and drifting so slowly that the middle remains livable while the edges shift. That's the pivot to fields that can set and slowly move these numbers, and to the idea that laws might be the local weather of deeper dynamics. The multiverse, scalar fields, and slow drifting laws. The laws are local weather. When fields move, laws are just the forecast. If the constants feel like knobs, who's turning them? The simplest answer isn't a committee of gods, it's fields.